Okay, again, my name is Frank Wood. I'm a professor at Oxford. I work on probabilistic programming, machine learning, artificial intelligence, Bayesian nonparametrics, a whole bunch of stuff. And it's really awesome to be here. It's a wonderful facility, a super awesome set of hosts, and an interesting opportunity to indeed share some surprising commonality between what we've been doing and what. So today we're going to cover three topics which are interconnected in an interesting way. It's going to be a long and interesting story, I hope. We're going to start with probabilistic programming. How many of you have heard of probabilistic programming? So we're going to talk a little bit about probabilistic programming, in particular a cutting-edge, state-of-the-art language that's been developed in my group. I'm going to talk a little bit about deep learning. Ganesh will give a lecture and a practical on deep learning. And then we'll finish the day with a lecture on inference compilation by Tuanang, who's sitting there in the back as well. And massive credit goes to those two because they've really done most of the work. So again, today we're going to try to get you to understand probabilistic programming in a general sense, and we're going to actually have you do some programming in the Anglican environment, which happens to be a Cloture environment, which happens to be a Lisp environment, so you're going to get to know a little bit about functional programming. We'll talk about deep learning and get you to do some stuff with PyTorch, but we're going to talk about it more generally in terms of automatic differentiation, a subject of which Ganesh is a world's expert. And then we're going to talk about a very recent but interesting combination of probabilistic programming, or inference, and deep learning, which is called inference compilation, which effectively gives you very, very rapid repeated inference, which we call amortized inference. Sorry about the slide here, but I want to lay out what I want you to get out of this lecture. I'd like you to understand probabilistic programming in general, sort of why we were interested in it, a little bit about its history, how it works. I want to show you enough about functional programming so that when you hit the exercises, you're not totally dumbstruck. I want to talk a little bit about and maybe give you some hints about how one might write your own probabilistic programs in practice. And I will assume, and I think appropriately given the level of the discussion in the lectures yesterday, that you know something about generative modeling, you know what inference and conditioning is, you know about approximate Bayesian computation, you've programmed in some language, and you know what a stochastic simulator is. Okay? So I think that's aimed correctly, but if I'm wrong, pull me aside later and we'll go over some stuff. So first question you should ask if you are unfamiliar is, what is probabilistic programming? It's an emerging field that sits at the intersection of machine learning, statistics, and programming languages, kind of pulling a little bit of each, a little bit of content from each. In particular, it's really about doing statistics, in particular Bayesian statistics, using the tools of programming languages, so compilers, formal semantics, code transformations, that sort of stuff. Okay? Intuitively, when we write simulators or when we write computer programs, we write some sort of program that has free variables or arguments or something like that. We plug in the values of those arguments, or you have a function, you put the value of the function, the arguments to the function in, you compute forward, you get an output. This is, of course, a simulator, a program, a stochastic simulator, whatever. Everybody looks miserable. Is everybody okay? Can everybody smile just for a second? Okay. All right. So we run this forward to get some sort of output, right? In statistics, we do something rather different. In statistics, we start with some data, observables y. Thank God we're all statisticians here, and we use y for observations. That's great. So our observations are y. And we say, OK, I've got some data set. I'd like to understand it. And what I'm going to do is I'm going to describe some sort of abstract, mathematically denoted generative model, generally speaking, and say, OK, what I'd really like to do is figure out what the latent variables are, parameters to this model that would explain the data well. Okay? So intuitively, probabilistic programming is about doing statistics using the tools of computer science. So we all know, thanks to the ABC connections here, that a model, stochastic simulator, they're pretty close to the same thing. Okay, so I don't have to convince you of that. That's great. So we're going to replace the denotation of a model from mathematical denotation, i.e. writing down equations and then solving Bayes' rule or deriving updates, with actually program text code. Okay, that's going to give us some advantages. But we're going to have the disadvantage of having to do Bayesian statistics, which is to say that we're going to start with a program and get its output. right? So we all know this as well. So if we're doing ABC, we effectively have the output of our simulator, and we'd like to figure out what parameters or settings of the latent variables in our simulator could have given rise to that output. And we use the tools of inference. You guys have been talking about approximate Bayesian inference, or approximate Bayesian computation, to characterize an approximation to the posterior. Our stuff can do this as well, but in general, we're going to just think about inference and whatever algorithms we can run in the space of models denoted as programs. Okay? Great. Questions so far? What denotes what? How do you find what? If you see a probabilistic program, sorry, I'm going to turn on my phone. Walking down the street, how do you know it's a probabilistic program? Well, it's got a couple of added constructs. So from what we saw yesterday, you would say an ABC program or something like that, a stochastic simulator, is a program where you can rip all of the random choices out, stick them outside, then condition on the values of those random choices, run forward, okay? That's not so different than a probabilistic program, except that our denotation is going to be a little bit richer in the sense that we're going to allow basically two things that are to be in the language itself, okay? So you guys might do stochastic simulation with randomness on the outside and then just a regular programming language for the simulator. We're going to say the language must have the ability to draw values at random from distributions. That's pretty common, and that's common to your situation as well. But we're also going to have the syntactic and semantic ability to condition values of variables in a program via observations, okay? That means that the language is actually going to have something like a conditioning operator or a factor operator or something like that, that says this is the output that the program generated. I also, by the way, I appreciate the fact that I get to speak in English to you. This is really wonderful for me because I only speak English. I also know that I speak really, really fast. So if somebody would like me to slow down at any point, please let me know. Excellent question. You're only allowed to condition at the end. You only get to see the output. You have no syntactic construct for observe. We have a syntactic construct for observe, and we can observe any point of the program's execution at any time and condition on that. Okay? So literally, observe is part of our language. Okay. That means that things like SMC-like algorithms become natural for us. They're just part of how we can do things. You'll see. So what are the goals of probabilistic programming? It's not so different to the ABC community and what we've talked about here, which is we have a bunch of simulators, a bunch of models. We denote them however we want. We're not going to denote them in graphical model form or whatever. We're going to denote them in some sort of abstraction layer in terms of some kind of programming language. And then we're going to automate inference. So our job is to provide to you inference engines that just do inference for you. Your job is to write models and so on and so forth. And of course, if this works, then we'll develop a community of people who are writing models and using our abstraction layer, and a community of people who are writing inference engines that can be tested against all of the models written there. But really what you get out of, at the end of the day is a hammer, right? Which is to say, once you understand what probabilistic programming is about, then you have an amazingly powerful tool that you can apply to solve all kinds of problems that you might not think are amenable to being solved by inference. Statistics does not have a lock on whose phone is that's beeping, by the way? Can you turn it down? It's not mine, I don't think. I try to turn mine down. If you've got phones, it's really very distracting. So statistics is not the only field that has entries in the field of probabilistic programming. So we talked about bugs, wind bugs. Maybe you've heard of JAG, STAN, Libby. How many of you have heard of Libby? Nobody? Okay, great. So statistics has a bunch of probabilistic programming languages that have been around for a while. But so too does the field of artificial intelligence. the field of programming languages, and very recently, in particular, machine learning has cottoned onto the idea of probabilistic programming languages. Let's look at what these look like and try to get you thinking about what probabilistic programming is like. We'll focus over here because I think this is a statistics model, so we'll look at bugs and maybe one stand model. So this is a bugs model, also a bugs program. It's not the entire thing. There's a data block and a params block up above, if you're familiar with it. But let's look at this program. So this says x is normally distributed with some parameters, and then for I equals 1 to n, y is distributed according to some parameter, some normal distribution with mean x and precision 1 over c. Okay, so you can more or less see just straight away, without knowing anything about the bugs language, that there's a correspondence between this model and this graphical model, where every one of these nodes is governed by a normal distribution, right? Okay. I'd like to say a couple of things about this. One is that this is a denotation of a model, right? I haven't told you anything about where conditioning happens or what observe is. So what's the syntactic representation of observe or conditioning in bugs? Only half of it's on the slide. What does the twiddle symbol mean?
Generated from, simulated from.
And? So it has a double meaning. You're absolutely right. So it's generated from, but it also means that generally speaking, you can score. And let's remember that we're going to blend between ABC and actually having likelihood. So this is not likelihood free here, right? So it means two things. One, that you can generate this value from this distribution, but it also means that if you have this value, you can score it under this distribution, right? You can compute the log probability of this output under this density in general, right? That's the lay meaning of the twiddle symbol or tilde symbol. I should point out that this is a little bit confusing, and one of the reasons why one might want to use a slightly richer and more formal semantics or syntax that supports a more formal semantics. But anyway, so in bugs, conditioning occurs when you have the values of some of these things defined in a data block above. If you have the values of y defined, then the language knows that I actually already have these values, so any value that I know I can condition on, and then I'm interested in any of the free variables in the expression, I would like the posterior distribution of those. So that's how you denote an inference problem in bugs. So I give you the values of some of the variables. Any free variable, I want the posterior distribution of. Great. So I'd like to say also that there are two ways of reading this program. How do you read this program? What does it correspond to? Or how could you evaluate this program? What does it mean to evaluate a program? It means to run the program. So how could you run the program?
What is the output?
Yeah, what's the output? Let's start with that. Yeah. Okay, so we have a, this is great. So the answer to this was the output is y. No. Okay, so that's really interesting. The output of this program is the posterior distribution of any free variable in the expression. Okay, so the output of this program will be samples of x. Okay, great. The next thing is, let's go with how do you evaluate this okay, great. Okay, some people are like, woo, what's going on here? Great, that's good, I'm getting your attention. Okay, so how do you evaluate the program? So I've just told you that let's go with your view. So you, I think, just said, let's run the program forward. Let's simulate x from normal, and then let's run this loop, and let's simulate a couple of values of y, and we can get a sample from the joint distribution that way, no problem, right? Is there another way to evaluate the program? What I'm hoping for, thank you for interacting, I appreciate that, free coffee for you. What I'm hoping for is, you can read this as build a node in a graphical model, call it x, and then for n times, build another node in a graphical model, call it y, and add an edge to x. Okay? So you could build an evaluator for this program that either runs it and generates samples, or you can build an evaluator that runs it and creates this graphical model. Right? And if you do that, then what you get is basically a bugs evaluator. Because what happens is the language is restricted, so there are no loops. All loops are bounded. This has to be a finite variable and non-stochastic. There's no branching. You can't write an if statement in bugs, right? Which means, at the end of the day, the model class that's denotable in a bugs program is a finite graphical model, i.e. a graphical model with a finite number of nodes. Okay? And the way you run a bugs program is called a non-standard interpretation of the program. You don't run it as at least these two participants looked at this program and said, I just run the program. The way you run it and the way it gets evaluated is it gets turned into this graphical model, and then a Gibbs sampler, a generic Gibbs sampler that can work on any graphical model, is run on that graph. Okay? So that's the evaluation model for bugs. Okay? Great. How about Stan? Yeah?
Just a general question.
Loudly so everyone can hear.
If you denote y as the data that we observe, and then in this notation we draw a new normalized, so normal distributed y.
Uh-huh.
Is there a collision?
Great. So the question was, if you draw a new value of y. Okay, so you're still, great. So this indicates that you're still in the I want to run this program forward. Okay? That's not how these programs are evaluated. They're evaluated by building the graphical model. And there can be no collision because if you know the value of y, you simply know the value at that variable. That variable in the graphical model is observed. You know its value. Right? We'll return. How about Stan? Anybody want to read this Stan model now that you know how to read bugs? Stan is the same language model. It has the same syntax or model denotation as bugs, effectively. Okay? It's very popular. As statisticians or data science people, you would be frankly idiotic not to use Stan. It's a very, very good package for doing statistical analyses in a very broad and interesting class of models. Okay, great. So what's this model? Let me read through it. So let's take the incorrect view of this model or the way to evaluate. Let's read it as an evaluation. It's not quite incorrect in it. So let's read this. So let's draw some first x from a normal distribution, and then for t equals 2 to t, let's draw the next x from a normal distribution parameterized by a linear multiple of the previous x plus some noise. And then for t equals 1 to t, I'm going to draw y from a normal distribution centered at x at the same time step. I've just given you a big hint with the time step. Okay. This is a Markov chain. Yeah. It's in particular a hidden Markov chain. Yeah. An HMM, but it's not really well, for a statistician, it's a hidden Markov chain. For a machine learning person, this would be a linear dynamical system. And let's say, again, the parameters are the x's, which means that I know the values of y. So I'm going to have a data block up here that says I know the values of y. What's the output of this program? The x's. Great. Okay? So again, let's not read this program as running forward. Let's read the program as denoting a conditional inference problem, a posterior inference problem. Give me the outputs of the program, the y's, and I would like to know, so is this the filtering distribution or the smoothing distribution? Not whatever. Great, fine. So So this denotes the joint posterior distribution of all of the x's. So this is the smoothing distribution, okay? All right? So this is a denotation. It can be a little bit confusing the first time you see it, but it's okay. Trust me, it's okay. All right? So,
But may I ask you something?
Of course.
If we just look at the box, how do we distinguish which one is given, which one we are conditioning?
so this is the problem with slides. If I could have code in front of you, then you would see that there's another data block up here that has the values of y's. And that's the same as here. We have a data block just like in bugs. You have data, you know, C, Y, blah, blah. Exactly. Exactly. Great. So here, and this is the first place we're going to touch automatic differentiation, just to throw it out there. Here, you can actually think about running this program forward, okay? Because Stan is set up, this is kind of crazy, in such a way that what it does is it uses Hamiltonian Monte Carlo for inference, right? And what Hamiltonian Monte Carlo really needs is the gradient with respect to the parameters of the log joint density. Okay? So you can interpret this program as a program which computes the log joint density. Instead of the output of the program, it just computes the log joint density. And if you use the tools of automatic differentiation, which Ganesh will talk about in the next slide, then you can automatically get that through a non-standard interpretation of this program. So you can run the program, get its gradient, done. So Hamiltonian Monte Carlo is basically rerun the program, compute the gradient of the log joint density, done. Unfortunately, this language has some relatively major restrictions as well. So it has the same restrictions as bugs, but you also can't use any discrete random variables. None. Okay? So this means that you're stuck with finite dimensional differentiable distributions, but that's basically every log linear model you can want. So you're okay, right? Certainly hierarchical regressions are fine here. Okay, and you can, in this framework, even still, you can do all kinds of automated inference algorithms, which are just non-standard interpretations of this program. I'll skip over this, but there are other ways you can do this as well. Obviously, there are message passing algorithms. If you know belief propagation or expectation propagation, you can do the same kind of trick where you run the program to generate a graph. In particular, in machine learning, infer.net is highly performant and runs expectation propagation on a factor graph produced by a non-standard interpretation of a probabilistic program. Sweeping away lots and lots of stuff, what this leaves us with is a set of programming languages and evaluators for the same down here that are restrictive in some kind of way, okay? That either only allow you discrete random variables and various restricted kinds of recursion, or over here, where effectively the languages have been restricted to allow you to run known inference algorithms. What we work on is pretty different, which fall in the family of higher order probabilistic programming languages, are unrestricted languages, i.e. we're going to allow you to use whatever kind of computer programming language you'd like to do your model denotation, and we're going to make inference work no matter what. So we're going to do non-standard interpretation of programs written in whatever language you like. And this means that you can contemplate writing down and doing inference in crazy models, okay? Really very interesting models as far as I'm concerned. Models where X, the latent variable, might be program source code, or a scene description for a graphics engine, or a policy and world, in particular if you're doing policy learning, or a cognitive process, or now here we're down into the ABC land, a simulator and its outputs, okay? And what we condition on in each of these cases is the output of the source code, or an image, or rewards, or something like that. I'll give you some examples. By the way, somebody needs to, I'm not watching the time at all, so I have absolutely no idea. If people can give me an idea, that would be great. So something that you will do in Twanan section, I think, the very last exercise, if you stick with this, you will become a bona fide member of the Russian mafia by the, are there any Russians here? If I've offended ethnically one, I know, but let's just say a mafia, not necessarily the Russian mafia, a mafia. Everybody will think Russian mafia now. I apologize for that, but that's okay. So let's say that you want, for some reason, to break CAPTCHA, Okay? One of the original ideas about probabilistic programming, one of the original example applications came from the MIT group, where they said basically, so here we go. How do you solve CAPTCHA? So I'm the Russian mafia. I come to you. I put a gun to your head. I say, I need you to break the CAPTCHA on this site because I want to spam about Trump and get him elected. You better get me into this site. I want thousands of accounts today. But you have to make it through the CAPTCHA wall. How do you solve it? I'm willing to take questions and commentary from the back. The back over here I already know the answer, so back there is good. This is a room of some of the smartest people in the world. You're telling me if I put a gun to your head, you couldn't solve CAPTCHA? You could try to use a hidden Markov model, but I'm not sure how that would work. Some ideas? ABC. Tell me.
You can just measure distance between distance.
Louder, yeah.
Measure distance between it. You create a model, like a code, right? A code which will simulate the thing. And that's your simulated model, and then just do ABC.
Okay, he said just do ABC. Does everybody understand how to do ABC? Excellent job yesterday, you all. Okay, so this is, okay, well, let's at least consider the two alternatives because you're going to see the two alternatives throughout the day, okay? So there's at least a couple of alternatives. One is the regression alternative. What's the regression alternative? Deep learning. What do you do in deep learning? You train models. How do you train models? What do you need? Huge amounts of training data. So if you're the guy with the gun to his head or the girl with the gun to her head, then you have to go take your gun and put it on the head of like 8,000 other people that go label CAPTCHAs as fast as you possibly can, and then hope that there's enough of them to put into your convnet to solve as a regression problem. So one requires huge amounts of training data, right? The other one is effectively ABC. And of course, we're actually going to solve this using ABC, using our languages. You will solve it today, if that's okay. And what you do is you write the simulator. You have a model of how a particular style of CAPTCHA is generated. That is a probabilistic program or a stochastic simulator whose output is the CAPTCHA. If you can write some sort of summary statistic to compare the outputs, and then use Bayes' rule effectively to invert. So here the scene description in a CAPTCHA is the sequence of letters effectively, and the output is the CAPTCHA image. And what you're after is P of X given Y. So if you're given either an ABC system or probabilistic programming system, a generative model of your design, and automated inference, then you can solve problems like this, right? Same goes for basically any kind of rendering setup, right? Now, there are computational problems and there are all sorts of issues, but here the observed image is this. The latent variables were a polygonal mesh description of a face, lighting, color, so on and so forth. And what you get out at the end of the day is a posterior distribution over that mesh, colors, lightings, so on and so forth. Okay? We can do recursive reasoning. So this is one relatively large departure. I won't stress this very much, but if you would like to have a model on which you condition on a mutually recursive reasoning process where you can observe states of the reasoning process as it evolves, then this is something that's going to be easier to express in something like this. But very similar to the CAPTCHA example, I think this is the most visually compelling and obvious of the examples of what's going on in probabilistic programming. So our Stanford collaborators are interested in procedural graphics, in particular constrained or directed procedural graphics. So the story goes like this. if you're building a forest for a video game, sorry you've heard this, but if you're building a forest for a video game, you don't like hire 1,000 people to make trees. You hire one procedural graphics person to write a stochastic tree generator, and then you run that stochastic tree generator 1,000 times, right? Okay. So a stochastic tree generator is just some sort of stochastic simulator that makes branching decisions and elongation decisions, and you can see the run of one such program in the shape of this tree, right? However, if you have some sort of directorial control, say for instance, I want trees that miss this thing, then you need to be able to condition the stochastic generative process on missing this thing, right? Which you could either do while the program is running or after the fact. And if you do it while the program is running, you get to be a little bit more efficient about inference. Okay? Is that clear? Other examples, and then we'll go into some stuff. Other examples include program induction. This is a fun one. This is more or less straight ABC as well. So here we have a prior over programs. Literally, we're writing programs. We're teaching a computer to write programs, right? So this is stuff that I did with one of my STAR students a while back. So that's a prior over programs. And what you see is the execution of this program. These programs are samplers themselves, okay? So if you run the program multiple times, you're going to get a distribution over samples, okay? What we're going to condition on is the output of the program being distributed in some particular way. So in particular, in this example here, we would like the output of the program, when repeatedly run, to look like this blue curve. So what we're showing over here are samples drawn from the posterior distribution of programs. Okay? And the ABC summary statistic here is a KS test statistic about distinguishability of the distribution of outputs from the generated program. Okay? Okay. So we've got probabilistic programming as an idea. We've got model denotation in terms of programming language. We've had a couple of examples of restricted programming languages. We've looked at those and we've thought about how to evaluate those programs in terms of turning them into graphical models or running Hamiltonian Monte Carlo on them. Then we said, what if we could lift those restrictions? Then these are the kinds of models we could anticipate or think about writing. The problem is that we can't write those in the original model, in the original languages, so let's talk about higher order languages and get you going. Now, there are 3 or 4 languages in this family now. Anglican, Church, Venture, Web People, Turing.
And if you're using ABC in a programming language framework, then LP is also another one that came out from LCP.
Do they have observes in the language?
They follow the stand scenario. Yeah, exactly.
Okay, great. Well, it would be great. I'd like to hear about it if there is. But anyway, because you're talking to me, you're going to get Anglican. So there are going to be syntactic differences, but semantically, these languages are kind of all the same. Which is to say that fundamentally, at the end of the day, they allow you to be very loose in your expression of the model because you're going to use some regular programming language as your denotation. The consequence of that is that the models induced include models with infinite numbers of random variables. Okay? So that you cannot now ever evaluate the language into a graphical model. Okay? So all of our inference algorithms are going to be ones that actually do regular program evaluation. You just run the program, but we're going to do it in such a way so as to return posterior samples rather than the samples from the joint. Okay? So if you're curious about how all these languages go together, this is the a language family tree. So in machine learning a while back, now it's been 10 years probably, there was a paper about church, which really was a paper that pointed out that you could do Bayesian nonparametrics in a probabilistic programming system by using a higher order language. Then a bunch of us broke away and started doing stuff. Vikash at MIT started VentureScript, and then we took their modeling language and made interpreted Anglican, and then abandoned the modeling language after we figured out what was really going on when we made probabilistic C. And then we switched over to a pure closure syntax. The Stanford folks branched off over here and then built a compiler for WebChurch, a compiler for web people, and then switched over to JavaScript. And then the two closest languages are web people and Anglican. The critical differences are the shaded region over here is compiled, which is to say very fast, performant. Back here, these are all interpreted languages, which are remarkably slow, actually. So for those of you who are not familiar, and this is the thing that I need to put in front of you, you'll struggle with it a little bit, we'll do our best to help you, is that Anglican, for various reasons, is more or less the same thing as Clojure. And Clojure is more or less the same thing as a Lisp. Okay, so Clojure is a functional, pure language that just-in-time compiles to the JVM, which means like not lots and lots of portability. But it does mean that syntactically it looks like a Lisp. And if you're used to infix notation, prefix notation can be a little bit confusing the first time you see it, particularly when you're exposed to functions as first-class objects. But prefix notation looks like this. This says add 1 and 1. Just basically take the plus and stick it in there. And subtract 3 from 10, and so on and so forth. So the first thing inside of any parenthetical expression is a function. And it's pretty clear that plus, if you think about it, is a function of 2 arguments, right? And this expression will evaluate to the symbol 2, or to the value 2, sorry. Branching is totally fine, and everything is an expression. So what you're seeing in this is basically an abstract syntax tree denoted syntactically. So plus, if 4 is less than 5, then 1, otherwise 2, then add whichever it is, which I guess would be 1, to 3, that should output 4. Okay? But this can be an expression, that can be an expression, that can be an expression, so on and so forth. So if is a special form, this is the predicate, this is the consequent, this is the alternative, so on and so forth. Like I said, we won't do too much of this. You'll see a little bit of it, but it's important that you are able to at least look at this and parse it and understand what's going on. There's a lot going on this line. Functions are first class. Okay? As soon as you do that, formally, I won't bore you with the details, then as soon as you make functions first class, then you're in the infinite dimensional model family denotation case, you're done. Okay? You're in our realm of complexity. So this is an anonymous function known as a lambda, if you're familiar with lambda calculus or Lisp. This function is a function of 2 arguments. That's a vector form. This is the syntax for it. You know how to read this expression already. This function computes x times 3 plus y, where the arguments are provided. This function takes 2 arguments. So the 2 arguments are 10 and 2. So this will run this anonymous function with these arguments, producing 32. Everybody see that? No problems with this? Seeing it, then writing it are maybe 2 slightly different things, but it won't be too bad. There are nice local bindings. So it's very close to math. We're going to get very close to mathematical notation, actually, if you think about it for a second. Like, it's nice to be able to define functions and move them around, because we do that all the time in mathematical notation. So actually, this Lispy thing is very similar to mathematical notation. Also, this let construct is extremely familiar to mathematicians as well, because we say, let x be 10, let y be 2. We've defined some variables, we've given them even values, and then we can evaluate some expression given those values. Okay, so these 2 things are roughly equivalent. It is a higher order language. The higher orderness doesn't really matter that much. It means that functions are first class, but it does mean that when you have first class functions, you can do nice things. I put these in front of you because the code examples will have these in it occasionally. So you can map a function across data, right? And you can reduce a function starting at some value over some collection. Okay, so if you're familiar with a map-reduce paradigm, this really comes from this higher order functional view of the world where map and reduce are fundamental operations, where you take this anonymous function or this lambda expression and map it over these vectors simultaneously, so on and so forth. Any questions about this, or is this just hideously boring? Hideously boring? Questions? Okay. All right. So that's I've just taught you how to program in Lisp and Clojure in 3 slides. Okay. The reality is that you're going to have to teach yourself, but we have a large number of workbooks set up for you to do that. Let's instead look at Anglican through a couple of examples, so that when you get into the workbooks, you can sort of see what's going on. So here is an Anglican program. Okay. And I'll highlight this relatively clearly in just a second, but everything inside of a def query is Anglican. It is not Clojure, it's its own language, it's different, it gets evaluated differently, has different semantics, everything, okay? So the name of this program or query is Gaussian model. It takes an argument, can be anything, but in this particular case, it's going to be observed data. Then we let x be a sample from a normal distribution with some parameters, sigma be a constant value of square root of 2, and then unnecessarily we use a higher order, well, it's actually not unnecessary, this is an interesting point, but we use a higher order function map to map a function of a single argument that calls observe normal, this is some distribution, value y over data. So data is going to be some list or vector or something like that. We're going to map this function which observes under some distribution here, each value in turn, and then the return value of this program is x. Okay? But of course, it would be very uninteresting to return x if the semantics of this program weren't give me the posterior distribution, because then x would just be a sample from the marginal of the joint distribution. But what this denotes, thanks to this syntactic construct observe, is the posterior distribution of x under this model given data. And this model, if you read it out, looks like this. X is normally distributed like this. And for some unknown number of yi's, all of them are normally distributed with mean x. Okay? And I would point out just subtly, most of you won't get this, but I just feel like pointing it out because it's true. The mere fact that we can process a data structure of unknown length and compose this distinguishes this kind of language already from bugs or Stan or anything like that, because we don't know the size of this data structure at compile time. We only know it at runtime, which means, in the worst case, that this data structure could be unboundedly large. Okay? Which means we can't compile this to a graphical model because we don't know how big that data structure is. Okay? Great. But if we give it a data set, I don't think we use this form very often, but basically you'll see lots of forms where we're going to draw samples from that model. So it'll be infer with some inference algorithm, something like that. So Gaussian model is the name here. Particle Gibbs is one of the 14 or 15 algorithms we have. They all have parameters. Particle Gibbs has some number of parameters, some number of particles. That's one of the parameters. And then there's a data set, and that data set is this. And then we can draw samples by repeatedly calling an anonymous function, which samples from the posterior. Okay? Easy peasy. Okay? So you write this, and you get inversion, no matter what this program is. And the critical part is that it's not just graphical models here, and I think we all understand this already, but it's instead any program that you can write in Anglican, which we've defined to roughly be any program that you can write in Clojure, which means any program that you can write in Java, which means any program that you can use remote procedure calls and so on and so forth to call out to whatever simulator you want, fine. Anything. Network interop, whatever. Doesn't matter. All works. Okay? And to be really pedantic, that is Anglican. Okay? That code we do all kinds of crazy things to that I don't have time to explain, but it would be really awesome to have an opportunity if you're curious. This code is technically Cloture, but the interop between the two is subtle and easy. Let's do a couple of examples. Everybody, I assume, is familiar with Bayes nets. Okay, great. So this is a canonical Bayes net example, sprinkler Bayes net. Let's say that we're eventually going to observe sprinkler and wet grass, those values. Great. So is cloudy, we just write this. Is cloudy is a sample from a flip distribution, which is just a coin with even weights. Is raining, conditioned on whether or not it's cloudy or not, is a sample from a flip distribution with different probabilities. Sprinkler, so on and so forth. You can see what's going on. At the very bottom, we observe from the sprinkler distribution. Oh, by the way, distributions are also first class, which is pretty cool, because you can define a distribution and then pass it around and manipulate it. Okay? So observe distribution sprinkler, observe wet grass. You can pass in different values and automatically get the posterior distribution on whether or not it's raining by calling do query or conditional or whatever, given different assignments to these arguments. Does that make sense? So this denotes a posterior inference problem. This is not ABC. We're actually going to do inference in this model. But if you write models that are ABC-like in the sense that you don't actually have a likelihood, but you impose some sort of distance or factor based on a summary statistic, you can write the same thing, and all the inference algorithms just work. Okay? So, yeah, 4 minutes? Are we operating on Swiss or Italian time?
It's okay. You have the tea time, then you can go.
Fine, okay. So here's an HMM. We saw an HMM in Stan, although the HMM in Stan was a linear dynamical system with all continuous, latent, and observed variables. This is a more traditional HMM. I would encourage you to read this and tell me what kind of HMM it is. I'll give you 30 seconds. It's a particular kind of hidden Markov model. Expect the answer from the far back left corner. Okay, let's look at it. The initial distribution is discrete, so that's some even across 3 possible things. The transition distribution is a function which takes a state, and then conditioned on the value of the state, returns a distribution which is either discrete 0, 1, 1, 1, discrete 0, 0, 1, or Dirac 2. Okay? There's an observation distribution which takes a state and returns a normal distribution with the mean given by the numeric value of the state. We have a couple of observations y1 and y2, x0, x1, and x2. x0 is a sample from the initial distribution, x1 is a sample from the transition distribution given the value of x0, x2 a sample from the transition distribution given the value of x1. Then we observe under the observation distribution and at the value given by whatever the state is at x1, the observation value y1, y2, so on and so forth. And we'd like the joint posterior distribution of x0, x1, and x2. Okay? What kind of HMM is this? Hint, look here. How about the Harvard professor? This is the number one thing you're not supposed to do at something like this, is you're never ever supposed to call on any of the senior people because they're all working on grant deadlines or something horrible like that. You know, I just violated the number one thing, so I'm not coming tomorrow, just so you know. Yeah. Anybody know what a left to right HMM is? It's an HMM in which you can only transition upwards in state value. Like, for instance, when you have chickenpox, I don't know what it's called in any other language, but you either have never had chickenpox, then you have chickenpox, but then you're in a completely different state because you can't get chickenpox again until you get old, in which case you can get shingles, right? All right, so you actually fundamentally change state, and you can never go back to the pre-never having had chickenpox state before, okay? So this is an HMM that only transitions from state 0 to state 1 or 2, and when you're in state 1, it only transitions to state 2, and when you're in state 2, it stays, okay? So this is a particular kind of model, okay? That's one hidden Markov model. What do we have when we have this sort of composable language approach to model definition, right? This is all HMMs, okay? We're done. We never have to write an HMM again, okay? And the reason is that we can parameterize things by distributions. They're first-class objects. That's totally fine, right? So this is more complicated, and I wish that I had more time to read through it, but it basically consumes the observations, samples, latent state, observes, but all of the distributions are passed in, and this is all composable, okay? So literally, this is it. If you parameterize this by data, initial distribution, transition distribution, observation distributions, that's it. Never have to write another one again, okay? Captcha breaking. Well, we've already discussed this. This is ABC. We're going to do this in the compiled inference bit at the very end, which is, there's a generative model. We'd like the text given the image. We're going to do some sort of ABC style likelihood down here by projecting the image into a lower dimensional space, putting some noise on it, so on and so forth. Great. Easy enough to do, particularly if you have a Java captcha renderer, which they happen to exist.
So if we don't know the model, how would you do this?
If you don't know the model, how do you do this?
Yeah, do you know the generative model for the captcha?
Well,
Maybe you have Russian option. Sorry, some of the exceptions.
sorry to all the Russians in the room. What if you don't have the generative model? Well, then, okay. Then we know that there's this is an excellent question. And it is a subject of fervid, active research in machine learning right now, which is effectively automated model learning, right? It's been around forever, but there is supervised learning on one end of the spectrum, which is you have training instances. There's fully unsupervised, which is what we're talking about, where you're responsible for generating data by writing the model yourself, period. And then there's a spectrum in between. And unfortunately, the spectrum in between is not well explored so far. But we can take that offline, and there's lots of very, very interesting research being done on this right now, in particular by Mr. Twanan back there. Yeah.
Just a general question, so but if you don't have a model, is it possible to use your sampling? I mean, the model is just there to generate new samples, also in ABC. Is it possible to make just resampling the data somehow in a smart way so that it gets...
I don't think the mafia would be very happy if you simply had a small number of captchas and you said, I'm going to break a new captcha by simply resampling the captchas that I have and hoping that one of them is close enough that it gives me the correct string.
Sure, I mean, it requires still a bunch of captures, but then it's just the model itself. Can it be the exception suite, but something like resampling?
As in bootstrap kind of idea? Is that what you have in mind?
Yeah,
Let's take this offline. This is a good coffee thing. So I think maybe I'll leave. Because of timing, I'll leave how it works completely.
I think you can just take another 10 minutes and we just make the coffee break 15 minutes, not half an hour. If you want.
That's okay.
If it's okay
Who would like to hear a little bit about how it works? All right, great. I mean, I can give you like a 3-hour talk on how it works if you'd like. In fact, you can do an entire DPhil with me, or a postdoc, just to throw that out there. Okay, so I've got 10 minutes, and that's just about enough time to do this. So this is not how it actually works, but it's really close to how it actually works. Okay? And in terms of getting it in your head, it should be enough for you to, say, for instance, to write your first version of a probabilistic programming engine or whatever. Okay? So because we can't make the graphical model because our programs, we know, allow for the denotation of models with an infinite number of random variables, the only thing that we can do is evaluate the program, precisely how you two thought about it in the beginning, and maybe most of you thought about it. Okay? So we're going to call this evaluation-based inference for higher order probabilistic programs. And the gist, the idea is to basically explore as many traces as possible intelligently. Okay? So we're going to run the program lots and lots of times. It's going to look, this first algorithm is going to look a ton like an ABC algorithm. That's one of the reasons why I've just left it at this and won't go into any of the sort of more fancy algorithms. But what we're going to do is we're going to explore as many traces as possible intelligently. Of course, each trace contains all the random choices made during the execution of the generative model, i.e. every sample statement that you hit, that's going to be a random variable, and you're going to get a value for that, right? So a trace is those choices made as the program runs forward, plus all the deterministic operations, plus one more thing, which is observe doesn't do anything. It simply computes a side effect, okay? And a side effect is a fancy name given to something computed during the execution of a program that you don't actually see as output, but the interpreter or evaluator uses to do something, right? Okay? So provided that we compute an interesting side effect, then we can actually combine the weighted traces probabilistically, coherently, and then we can report the return value of the program or a projection over the traces, which is just which is the same thing, with a correct probabilistic semantics. So to give you a sense of what a trace is about, here's a program. T1 equals 3. X1 is a sample from a discrete distribution where we repeat T1 3 times, so it's basically uniform over 3 possible outcomes, 0 to 2. If x1 is not equal to 1, then t2 is a deterministic operation on x1. We add 7 to it, and then x2 is a sample from a Poisson distribution t2. Just some silly program, okay? So we can look at what the possible execution traces of this program are. T1 is 3. X1, the value of x1 is sampled from a discrete distribution, again, with support 0, 1, 2. Then if x1 is not equal to 1, this branch dies. If x1 is not equal to 1, then t2 is x1 plus 7, and x2 is a sample from a Poisson distribution with that parameter. So x1 here was 0, x1 plus 7 is 7. This value is Poisson distributed with rate 7. This value is Poisson distributed with rate 9. And now we have an infinite branching factor. So again, straight away, you can see even in this program, you can't write down the graphical model because there are an infinite number of random variables, okay? Or random variable values and so on and so forth, okay? So you can think of this as a many worlds execution path. Every stochastic choice leads to a branching of the possible execution paths of the program, okay? Great. There's no observe here, so if you were to run this, this would just generate samples from this stochastic simulator. If we stick at the very end of it and observe, which this could be an ABC likelihood, or it could be an actual observe in a model. Either way, we have to deal with both in our setting. Then let's say that we observe x2 is close to 1. Okay, so the value of x2 is close to 1. What does that say about the value of x1? Is x1 more likely to be 7 or 9? Well, the value of 1 under the Poisson PDF parameterized by 7 is higher than the value of 1 under the Poisson PDF with parameter 9. So the weight accumulated on this trace needs to be back-propagated up these traces, basically, or assigned to these traces such that this trace has higher probability than this trace in the posterior. Ergo, sorry to use that, ergo, the value of that x0, or the probability that x1 is 0, is greater than the probability that x2 is 0. If I said anything other than that, then I said something totally idiotic. Thank you very much. The probability that x1 is 0 is greater than the probability that x1 is 2. Now I think I said it correctly. By virtue of the fact that we've observed that x2 is close to 1. Right? This is the definition of inverse computation. It's the definition of, or the idea of inverse probability, or whatever. Okay, but the critical part, maybe the only part, is that observe didn't do anything. It just computed a side effect. And the side effect is graphically illustrated by the size of these balls here. That's all. Okay? So the program would continue executing, but we would continue accumulating weights on each of the execution paths. Right? Great. So now that you've got that picture in your head, it's really easy to see what's going to go on. Every trace consists of some number of observes, n. We're going to call these g. So this is going to be g. These are the distributions under which the observes occurred. Phi are going to be the parameters of those distributions. And y are going to be the observation values themselves. A sequence of m samples. F is the distribution from which the mth sample is drawn from. Theta is the parameters of that. And the sample values, i.e. the primary stochastic constituency of the traces, are these x's. I should point out, condition on the sample values, the entire computation is deterministic. So if you give me all of the choices of the values of the traces of all the random variables, it's just a regular straight line computer program.
So to go back, if you want to put this in the programming that you show us at the very beginning, would be like y as distribution g parameterized through phi.
Yep.
X as distribution f parameterized through theta.
Yep.
And y is given, and we want to have x given phi.
That's right. And that's exactly where I'm going to go here. But if you've got that in your head, that's perfect. So the trace probability, what we're going to define as the probability of any particular trace in whatever language, higher order, who cares, is going to be this. Gamma of x is defined as the joint probability of x and y, and we're going to always have the values of y. So this is totally fine. Y is not a free variable. Is exactly as was just described. It's the product over n of these g's, where we're evaluating y under the parameters phi, and the product of m f's, where the x's are governed by some distribution f with parameter theta. Okay?
Isn't there an x in the g as well? I mean, this would
Great.
be decouples, right?
Absolutely. So this is, when you look at probabilistic programming literature, notation, whatever, we often compress these things such that you can actually read them, because the actual dependency structure is totally crazy. Because, for instance, phi is of course a function of all of the x's, because there could be any deterministic computation that you want in there. This notation says the actual distribution itself, of course, can be a function of the state, because you can switch based on an if statement which distribution you're actually drawing a random variable from, for instance, right? Same thing, or I guess those are which ones you're observing a value from. The same thing over here. So the dependency structure is, of course, dependent on the entire execution state of the program up to scoping. That make sense? Okay.
So this would be the general hidden Markov model structure that you were talking about. This is
It's more than that. So I would say that a probabilistic program is a hidden Markov model where the state of the hidden Markov model is the entire state of the evaluator, whatever that happens to be. Roughly speaking, the state of a probabilistic program, if, say, for instance, you were writing in C and you are running forward, is the entire memory space and set of register values and so on and so forth of the forward executing program.
For example, you have no arrow that goes from y back to the axis. So
That's very much on purpose. So you can't write ARMA models.
right, but so that would be, suppose I'm executing at x5.
Uh-huh.
So in my memory, there's everything that's on the left.
This stuff here.
Yes. Yeah.
So the critical point, okay, this is an excellent question. It's a really excellent question. There's a difference between the values of y, which are available everywhere, and the observed statements. So in fact, you can write ARMA models. It's not a problem because the values of y are they're just values. The dependency on these observed statements is very intentionally like this, because we need them to hang off the end, okay? But that doesn't actually restrict you in any real way. And we can talk about that. That's actually quite a subtle point. The reason why we have to do that is very, 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 very subtle. Okay, the inference goal, we're talking about posterior inference. So how do we turn a program around from running it forward? There are lots of ways to do this. Some of them are quite sophisticated. We're going to talk about the easiest way to do it, which is very close to ABC, in particular what you talked about. Thank you, Carla talked about yesterday. So the posterior distribution that we're after is the posterior distribution of x given y, and that's just the joint over some normalization constant, okay? Where the normalization constant is the evidence, which looks like this. And what we're after is the output, some expectation of some query computed on x, which is, of course, just this integral, as we all know, okay? Great. What we're going to talk about is likelihood weighting. This Q right here is going to come up a lot later on today, okay, in the form of importance sampling, okay? So we're not going to talk about there are three really basic algorithms that can be used in probabilistic programming systems that are evaluation-based. Metropolis-Hastings and sequential Monte Carlo are much more performant than likelihood weighting, but likelihood weighting will give you a sense of what's going on. So let's talk about likelihood weighting. It's a very simple idea. Run the program k times, okay? By simulating from the prior, okay? So our Q in this is simply going to be run the program forward. Ignore every observed statement. Don't do anything with them, just run the program forward, okay? So this is our proposal distribution. Conveniently, when you choose that form of the proposal distribution, we can accumulate weights for importance sampling in this framework, which are the joint over the proposal distribution, which only leaves likelihood terms. Okay? Great. So you run the program forward. When you hit an observed statement, you very simply compute the value of the log PDF at that observed point. Right? Then we can use that in Monte Carlo integration because we're going to get some unnormalized weights for every trace out. And any expectation we'd like to compute against the posterior samples or against the posterior distribution can be approximated using the strong law of large numbers by this weighted sum of queries evaluated against samples drawn by running the program forward and accumulating as a side effect the observed likelihood. Okay. I said that really fast because we didn't have a huge amount of time, but how many of you could implement this version of a probabilistic programming system now? One, great. Two, and well, yeah. So let's think through what this means. This is dead simple. Like there's a whole bunch of unnecessary math up here, right? It's dead simple, okay? Okay, first of all, you do have to know how to write an evaluator. Okay, how do you write an evaluator? Okay, that's not so hard. You go in and you look at the expression and you write an interpreter that says, okay, I see +1, 3. I'm going to replace that with 4, and I'm going to do that recursively through all the expressions. Okay, that's easy. Okay, so you write an evaluator, you write an interpreter. running the interpreter says, replace this expression with a value. If I see a sample expression, I just sample from the denoted distribution, no problem, right? And I can recursively generate the value of an expression, i.e. a program, by going down into the expression, computing the subparts, and then bubbling back up. What do you do when you hit an observe? You just compute the log probability of the observed value, and you keep it around. That's why we call it a side effect. Okay, so you write an interpreter, you interpret all of the sub-expressions, so on and so forth, sampling when you hit sample statements. When you hit an observed statement, you just say, oh, okay, I need to keep something around. That's going to be my unnormalized log probability. I'm going to just add that to the value as I'm running forward. Okay, so I do this, and I write an evaluator that just runs the program exactly as you would expect, but when it hits an observed statement, it saves one extra number per observed statement. Okay? And I run a program, and I get an extra number out. So I get the return value for the program, plus I get a side effect, the log probability of the sum log probability of the observes. Okay? Then I run the program again. I can run it 8 billion times in parallel. It doesn't really matter. I'm going to get a sample value, a trace out, a return value, plus an unnormalized weight. That's it. Super simple. By the way, you can do this in a compiled environment as well, provided that you just implement an observe method that writes somewhere the side effect, no problem, right? And what you have is something like this. You basically have the execution of the program which generates the return value, and it steps aside for just a second every time it hits an observed statement and saves a side effect. That's it. Okay? And you can go much, much further with this than you think you can. So where are we? Probabilistic programming has been around for a really long time. The tool maturity is actually really probably beyond this now. The systems are pretty well put together. There are a couple of put-offs, which is to say that some highly optimized models, if you want to do, for instance, latent Dirichlet allocation or something like that, you probably don't want to write that in Anglican. It's not going to be pretty. But you can certainly use the systems now. There's an opportunity, there's an HPC opportunity in a big way, because most of the algorithms that we write are amenable to parallelization, but we're going in a slightly different direction. So one of the exercises, just for the fun of it, that you'll encounter is another ABC exercise. I'll leave you with some pretty pictures on the way out, and then you're set up for deep learning and inference compilation later, and I'll talk about those in just a second. We might want to do some sort of inference task like this, where we want to put these balls in this box. Okay? And I would encourage you to think about how to write a program that, under a deterministic simulator, figures out how to place a percentage of the balls in the box using generative modeling and conditioning. Okay? So this is part of the set of exercises that we'll do next. It is the last of the exercises, but it's definitely reachable in a very short period of time. I have lots of people to thank. These guys have all left, but David Tolpin in particular really is the architect of the modern version of Anglican. Hong-Suk Yang is the programming languages guy. He's gone to KAIST. I forgot to put the little thing there. And of course, these two guys are in the back. I have a couple of postdoc openings. If you're interested, please let me know. And this is the URL again. It's the same as this. What we should do is just get started with the exercises. I think the exercises come next, I think. No, I thought there was this and then an exercise. I can't remember. I think it's this, then an exercise, then a talk, and then an exercise, and then a talk and an exercise, but I don't know.
That's what the plan. I don't know.
Well, we can rearrange it.
So it's entirely up to you, but get started. Make sure that you have this sort of set up so that you can actually run the Gorilla REPL and start coding. And just to link everything together, so the problem with inference is that it's inference. Okay? As much as we love ABC and as much as we love other forms of inference, it's inference. It's slow. Right? It doesn't work in high dimensions. There are all sorts of issues. In particular, it's really, really bad if you want to do repeated fast inference, say for instance in the CAPTCHA case, right? It will be insufficient if you write a generative model and it takes, for instance, half a day to solve every CAPTCHA. Not good enough, right? You really need a system that can solve a CAPTCHA very, very quickly. Or if you're building an AI application and you would like to use inference as part of the tool set for the AI agent, i.e. it would like to do inference in this particular program, but it needs to do it rapidly because it's using it in some sort of online decision-making process. What we need to do is we need to develop a tool set that allows us to take an arbitrarily described inference problem and automatically turn it into something that performs inference in that model very, very rapidly. Okay? And the remainder of the lectures from us are going to be about how do you take a language like this, or an inference problem denoted in a language like this, marry it to the tools of deep learning, okay, which Ganesh will talk about, to produce an artifact through a crazy new kind of compilation, which performs very, very rapid inference in whatever program it is that you specify. Okay? And again, there's an HPC opportunity here because that training or compilation of that artifact is enormously computationally intensive. However, what you get out at the end of the day is something pretty cool, actually, which it says you write a program, you compile it for a really, really, really long time, which Ganesh and Tuanan will talk about, producing a deep network artifact, which Ganesh will talk about, automatically, that performs inference really, really fast. Okay? So that's where we're going. But to get started and to appreciate all of that, you have to get used to denoting inference problems in our language. So the first step will be learn a little bit of Cloture. The second step will be learn a little bit of Anglican. The third step will be try to write an Anglican program. Then Ganesh will introduce you to PyTorch, which you will not actually have to really code in yourself because we'll do that for you thanks to this inference compilation thing. But you'll learn a little bit about deep learning, automatic differentiation, so on and so forth. And then at the very end, with Tuanan, you'll hear about inference compilation, and then you'll figure out and learn how to use the tools of a higher order language plus inference compilation to solve inference problems fast in a repeated fashion. So thank you very much for your attention. Thank you for your interaction. And I look forward to helping you get into all this. Thank you very much. Well, so if we're doing ABC, we effectively have the output of our simulator, and we'd like to figure out what parameters or settings of the latent variables in our simulator could have given rise to that output. And we use the tools of inference. You guys have been talking about approximate Bayesian inference, or approximate Bayesian computation, to characterize an approximation to the posterior. Our stuff can do this as well, but in general, we're going to just think about inference and whatever algorithms we can run in the space of models denoted as programs. Okay? Great. Questions so far? What denotes what? How do you find what? If you see a probabilistic program, sorry, I'm going to turn on my phone. Walking down the street, how do you know it's a probabilistic program? Well, it's got a couple of added constructs. So from what we saw yesterday, you would say an ABC program or something like that, a stochastic simulator, is a program where you can rip all of the random choices out, stick them outside, then condition on the values of those random choices, run forward. Okay? That's not so different than a probabilistic program, except that our denotation is going to be a little bit richer in the sense that we're going to allow basically two things that are to be in the language itself. Okay? So you guys might do stochastic simulation with randomness on the outside and then just a regular programming language for the simulator. We're going to say the language must have the ability to draw values at random from distributions. That's pretty common, and that's common to your situation as well. But we're also going to have the syntactic, and you put the value of the function, the arguments to the function in, you compute forward, you get an output. This is, of course, a simulator, a program, a stochastic simulator, whatever. Everybody looks miserable. Is everybody okay? Can everybody smile just for a second? right? Okay. All right. So we run this forward to get some sort of output, right? In statistics, we do something rather different. In statistics, we start with some data, observables y. Thank God we're all statisticians here, and we use y for observations. That's great. So our observations are y. And we say, OK, I've got some data set. I'd like to understand it. And what I'm going to do is I'm going to describe some sort of abstract, mathematically denoted generative model, generally speaking, and say, OK, what I'd really like to do is figure out what the latent variables are, parameters to this model that would explain the data well. Okay? So intuitively, probabilistic programming is about doing statistics using the tools of computer science. So we all know, thanks to the ABC connections here, that a model, stochastic simulator, they're pretty close to the same thing. Okay, so I don't have to convince you of that. That's great. So we're going to replace the denotation of a model from mathematical denotation, i.e. writing down equations and then solving Bayes' rule or deriving updates, with actually program text code. Okay? That's going to give us some advantages. But we're going to have the disadvantage of having to do Bayesian statistics, which is to say that we're going to start with a program and get its output, right? So we all know this is probabilistic programming or inference, and deep learning, which is called Inference Compilation, which effectively gives you very, very rapid repeated inference, which we call amortized inference. Sorry about the slide here, but I want to lay out what I want you to get out of this lecture. I'd like you to understand probabilistic programming in general, sort of why we were interested in it, a little bit about its history, how it works. I want to show you enough about functional programming so that when you hit the exercises, you're not totally dumbstruck. I want to talk a little bit about and maybe give you some hints about how one might write your own probabilistic programs in practice. And I will assume, and I think appropriately given the level of the discussion in the lectures yesterday, that you know something about generative modeling, you know what inference and conditioning is, you know about approximate Bayesian computation, you've programmed in some language, and you know what a stochastic simulator is. Okay? So I think that's aimed correctly, but if I'm wrong, pull me aside later and we'll go over some stuff. So first question you should ask if you are unfamiliar is, what is probabilistic programming? It's an emerging field that sits at the intersection of machine learning, statistics, and programming languages, kind of pulling a little bit of each, a little bit of content from each. In particular, it's really about doing statistics, in particular Bayesian statistics, using the tools of programming languages, so compilers, formal semantics, code transformations, that sort of stuff. Okay? Intuitively, when we write simulators or when we write computer programs, we write some sort of program that has free variables or arguments or something like that. We plug in the values of those arguments, or you have a function, and semantic ability to condition values of variables in a program via observations. Okay? That means that the language is actually going to have something like a conditioning operator or a factor operator or something like that, that says this is the output that the program generated. I also, by the way, I appreciate the fact that I get to speak in English to you. This is really wonderful for me because I only speak English. I also know that I speak really, really fast. So if somebody would like me to slow down at any point, please let me know.
The difference was not very clear to me. Simulate models and program.
Excellent question. You're only allowed to condition at the end. You only get to see the output. You have no syntactic construct for observe. We have a syntactic construct for observe, and we can observe any point of the program's execution at any time and condition on that. Okay? So literally, observe is part of our language. Okay. That means that things like SMC-like algorithms become natural for us. They're just part of how we can do things. You'll see. So what are the goals of probabilistic programming? It's not so different to the ABC community and what we've talked about here, which is we have a bunch of simulators, a bunch of models. We denote them however we want. We're not going to denote them in graphical model form or whatever. We're going to denote them in some sort of abstraction layer in terms of some kind of programming language. And then we're going to Okay, again, my name is Frank Wood. I'm a professor at Oxford. I work on probabilistic programming, machine learning, artificial intelligence, Bayesian nonparametrics, a whole bunch of stuff. And it's really awesome to be here. It's a wonderful facility, a super awesome set of hosts, and an interesting opportunity to indeed share some surprising commonality between what we've been doing and what. So today we're going to cover 3 topics which are interconnected in an interesting way. It's going to be a long and interesting story, I hope. We're going to start with probabilistic programming. How many of you have heard of probabilistic programming? So we're going to talk a little bit about probabilistic programming, in particular a cutting-edge, state-of-the-art language that's been developed in my group. I'm going to talk a little bit about deep learning. Ganesh will give a lecture and a practical on deep learning. And then we'll finish the day with a lecture on inference compilation by Tuanang, who's sitting there in the back as well. And massive credit goes to those two because they've really done most of the work. So again, today we're going to try to get you to understand probabilistic programming in a general sense, and we're going to actually have you do some programming in the Anglican environment, which happens to be a Cloture environment, which happens to be a Lisp environment, so you're going to get to know a little bit about functional programming. We'll talk about deep learning, get you to do some stuff with PyTorch, but we're going to talk about it more generally in terms of automatic differentiation, a subject of which Ganesh is a world's expert. And then we're going to talk about a very recent but interesting combination of probabilistic